Jamming, possible solutions for jamming, types of jamming, proactive jammer and countermeasures, reactive jammer and countermeasures, tampering attack and its countermeasures, black hole attack and its countermeasures, flooding attack and its countermeasures. Jamming. What is jamming? This is one of the denial of service attack in which the adversary attempts to disrupt the operation of the network by broadcasting a high energy signal. Jamming attacks in wireless sensor networks, classifying them as constant, that is, corrupts packet as they are transmitted, deceptive, that is, sends a constant stream of bytes into the network to make it look like legitimate traffic, random, that is, randomly alternates between sleep and jam to save energy, and reactive, that is, transmits a jam signal when it senses traffic. Jamming attacks in AWSN classifies them as constant, deceptive, random, and reactive. To defend against this attack, we use spectrum techniques for radio communication. Handling jamming over the MAC layer requires admission control mechanism. Possible solutions for jamming. Jamming in wireless network is defined as the disruption of existing wireless communications by decreasing the signal-to-noise ratio at receiver sides through the transmission of interfering wireless signals. Jamming can be done at different levels, from hindering transmission to distorting packets in legitimate communication. Jamming makes use of intentional radio interferences to harm wireless communication by communicating medium busy, causing a transmitter to back off whenever it senses busy wireless medium or corrupted signal received at receiver. Jamming mostly targets attacks at the physical layer, but sometimes cross-layer attacks are also possible. Types of jammers. Jammers are classified into proactive jammer, reactive jammer, which are furthermore classified into constant jammer, deceptive jammer, random jammer, reactive RTS, CTS jammer, reactive data acknowledgement jammer. Jammers are malicious wireless nodes planted by an attacker to cause international interference in a wireless network. Depending upon the attack strategy, a jammer can either have the same or different capabilities from legitimate nodes in the network which they are attacking. The jamming effect of a jammer depends on its radio transmitter power, location, and influence on the network or the targeted node. A jammer may jam a network in various ways to make the jamming as effective as possible. Basically, a jammer can be either proactive and reactive. Let's see one by one. Proactive jammer. Proactive jammer, it transmits the jamming or the interfering signals whether or not there is data communication in a network. It sends packets on random bits on channel it is operating on, putting all the other nodes on that channel in non-operating modes. However, it does not switch channels and operates on only one channel until its energy is exhausted. There are three basic classifications of proactive jammer that are constant, deceptive, and random. Constant jammer emits continuous random bits without following the CSMA protocol. A constant jammer prevents legitimate nodes from communicating with each other by causing the wireless media to be constantly busy. This type of attack is energy inefficient and easy to detect, but it is very easy to launch and can damage the network communication. Deceptive jammer. It sends a constant stream of bytes in the network to make it look like a legitimate traffic. Random jammer. It intermittently transmits either random bits or regular packets into network. It continuously switches between two states, sleep phase and jamming phase. It sleeps for a certain time of period and then becomes active for jamming before returning back to the sleep state. Reactive jammer. Reactive jammer starts jamming only when it observes the network activity occurs on a certain channel. As a result, a reactive jammer targets on compromising the reception of a message. It can disrupt both small and large sized packets. Since it has to completely monitor the network, reactive jammer is less energy efficient than random jammer. However, it is much more difficult to detect a reactive jammer than a proactive jammer because PDR, packet delivery ratio, cannot be determined accurately in this practice. There are two different ways to implement a reactive jammer. They are reactive RTS-CTS jammer and reactive data acknowledgement jammer. The first in this jams the network when it senses a request to send message is being transmitted from a sender. It starts jamming the channel as soon as RTS is sent. In this way, the receiver will not send back CTS, that is clear to send reply, because RTS packet sent from the sender is distorted. Then the sender will not send data because it believes the receiver is busy with another ongoing transmission. Reactive data acknowledgement jammer. It jams the network by corrupting the transmission of the data or acknowledgement packets. This type of jammer can corrupt data packets, or it waits until the packets reach the receiver and then corrupts the acknowledgement packet. The corruption of both data packet and acknowledgement message will lead to retransmission at the sender end. Countermeasures for proactive jammer. In proactive jamming, the jammer chokes the bandwidth so that a transmitter is unstable to transmit. Therefore, a carrier sensing threshold can be used to detect such type of jammer. When jamming is detected, nodes in the network can map the jammed area and reroute traffic, switch channel, or perform spatial retreat to counteract this jamming act. Countermeasures of reactive jammer. Reactive jamming detection using BER, bit error rate. It is used to detect jamming using the bit error rate for reactive jammers and keeps the received signal strength, that is RSS, low by introducing disruption in a packet. By looking at RSS, that is received signal strength, of each bit during the reception, it identifies the cause of bit errors for individual packet using predetermined knowledge, error correcting codes, that is ECC, or wired node chain system. If error is due to weak signal, the RSS should be low. If the RSS value is high for a bit error, there are external interferences or jamming. Assuming nodes can access the expected local interference, the sequential jamming probability test calculates the marginal likelihood of error due to 10 unintentional collisions. If this value is less than the log of ratio of targeted probability for a missed alarm to be targeted probability, then the jamming and an alarm is raised. If the marginal likelihood is less than the ratio, there is no jamming and sequence is reset. There is also a probability that no conclusion is made until there are more conclusion evidence of the jamming. Tampering attack and its countermeasures. An attacker can damage or replace sensor and computational hardware and the program codes, or remove sensitive materials like cryptographic key to allow unrestricted access to higher level of communication as shown in the figure at the side. Thereby, these tampering nodes interference in the physical access of the nodes. Now the countermeasures are: some attacks in the physical layer are quite hard to cope up with. For example, after sensors are deployed in the field, it is difficult or infeasible to prevent every single sensor for device tampering. Therefore, although there are some mechanisms that attempts to reduce the occurrence of attack, more of them focus on protecting information from divergence. Access restriction. Obviously, restricting adversaries from physical accessing or getting close to sensor is effective on tampering attack. It is good to have such restrictions if we can, but unfortunately, they are either difficult or infeasible in most cases. Therefore, we usually have to fall back on another type of restrictions that includes communication media access restriction. A few techniques exist nowadays that prevent attackers from accessing the wireless medium in use, including sleeping, hibernating, and spectrum communication. These techniques use either analog scheme where the frequency variation is continuous or digital scheme where the frequency variation is abrupt. By this way, attackers cannot easily locate the communication channel and are thus restrained from attacking. The spectrum communication are not yet feasible for AWSN that are usually constrained in resources. Bidirectional antenna is another technique for access restriction. Then comes our encryption. In general, cryptography is all-purpose solution to achieve security goals in AWSN. To protect data confidentiality, cryptography is indispensable. Cryptography can be applied to the data stored on sensors. Once data are encrypted, even if the sensors are captured, it is difficult for adversaries to obtain useful information. A more costly encryption can yield higher strength, but it also drains the limited precious energy faster and needs more money. More often, cryptography is applied to data in transmission. There are basically two categories of cryptography mechanism: asymmetric and symmetric. In symmetric mechanism, the keys used for encryption and decryption are different, allowing for ease key distribution. It usually requires a third trusted party called certificate authority to distribute and check certificates so that identity of the user using a certain key can be verified. However, due to the lack of priori trust relationship and infrastructure support, it is infeasible to have certificate authority in AWSN. Furthermore, asymmetric cryptography, it usually consumes more resources such as computation and memory. In comparison, symmetric mechanisms are more economical in terms of resource consumption. As long as two nodes share a key, they can use this key to encrypt and decrypt data and securely communicate with each other. Black hole attack and its countermeasures. Black hole attacks under the DOS attack in the network layer of OSI model. In this kind of attacks, the malicious nodes forgery other nodes by announcing a shortest false route to the destination, then attracts additional traffic and drops continually the packets. During data transmission, the source node sends a route request RREQ message to all the nodes including malicious node. Given that a malicious node may become active by receiving route request message and replies using route reply message. It attracts additional traffic by falsely claiming the shortest route to the destination. This causes blocking and increasing the energy consumption in node, leading to information of routing holes which disturb or stop the network functionality. Consider the figure shown that illustrates the black hole attack. While the source node A broadcast and route request message to discover the route for sending packets to destination node C, and route request broadcast from node A is received by neighboring node B, D and the malicious node E. The route reply message sent by the malicious attacker node E is the first message reaching the source node. This last updates its routing table for the new route to be intended node destination, discarding route reply message from the neighboring nodes. That includes the actual node destination and starts sending the buffered data packets immediately. In the same time, the black hole node drops all coming data packets rather than forwarding it. So black hole attack schematic illustration using route request and route reply packets are seen. The countermeasure includes routing access restriction, false routing information detection. Routing access restriction. The routing may be one of the most attractive attack targets in WSN if we can exclude attackers from participating in routing process, that is, restrict them from accessing routing. A large number of attacks in the network layer will be prevented or alleviated. Multipath routing is one of the methods to reduce the effectiveness of attacks launched by attacker on routing path. In these schemes, packets are routed through multiple paths. Even if the attacker on one of the paths breaks down the path and the routing is not necessarily broken as the path still exists. This alleviates the impact of routing attack, although does not prevent these attacks. A general way is to use authentication method. With authentication, it can be easily determined whether the sensor can participate in routing or not. Authentication can either be end-to-end or hop-to-hop. In end-to-end authentication, the source and destination share some secret and can thus verify each other. When a node receives a routing update, it always verifies the sender of the update before accepting the update. In hop-by-hop authentication, each message is transmitted in authenticated hop-by-hop. Therefore, the trust between the source and the destination is built upon. Data are authenticated hop-by-hop between associated nodes until they reach the base station. Hop-by-hop authentication can be combined with multipath routing. These paths can be physical, meaning that the messages are routed through multiple physical different communication paths. The second is the false routing information detection. Sometimes attackers do not have chances to send false routing information in the network. Example, during the route discovery stages, if the false information does not lead to network failure, such as broken routes, we really cannot do much about it. Otherwise, we can apply the idea of misbehavior detection method. For example, watchdog or IDS stands for Intrusion Detection System, may find that some nodes fail to route messages along the routing path due to the wrong information it keeps. This anomaly of route failure may trigger out an alarm. Nodes can start to trace the source of false routing information. The reputation can also be maintained depending on whether nodes are providing valid routing information.